This happens in shallow water. Sometimes in less than 1 meter of depth water, you could wade through barefoot. The killer weighs less than 200 grams, about the mass of a small apple. It moves slower than a crawling baby, and yet its venom can stop a human heart faster than many snakes. This isn't a jellyfish. It isn't an octopus. It's a snail. Not the kind creeping across your garden wall, but its aquatic relatives. Sea snails, especially cone snails, produce some of the most complex and lethal venoms ever evolved. Venoms so precise they can switch off pain, paralyze muscles, and silence the brain molecule by molecule. A single cone snail strike can deliver a cocktail of hundreds of toxins, each targeting a specific nerve channel. Some act faster than a gunshot reflex. Others shut down breathing without triggering pain, meaning victims may not realize what's happening until it's too late. By comparison, most land snails are harmless, slow, soft-bodied, chemically defenseless. If one crawls across your skin, nothing happens. So why does moving into water transform snails into biochemical assassins? Around halfway through this story, the mystery deepens because today we're exploring why aquatic snails became vastly more deadly than their land-based cousins, and what that says about evolution under pressure. Scientists still debate parts of this transformation. We've never witnessed it happen, but the evidence, venom genes, fossil shells, human fatalities points to a brutal evolutionary arms race. The real question is this: what kind of world turns a snail into a weapon? Predation changes everything. For most of their evolutionary history, snails were simple grazers, slow bodies, scraping algae, fungi, or decaying plant matter. On land, that lifestyle still works. Movement is slow for everyone. Chemical signals diffuse poorly in air. A snail can survive by hiding, retracting into its shell, and letting time do the rest. Water is different. In water, speed matters. So does chemistry. Molecules spread instantly. Predators come from every direction. And if you're soft, slow, and exposed, you don't get a second chance. Aquatic snails faced a brutal equation: either become food or evolve a way to stop predators. Capture prey before contact even finishes. Some lineages solved this mechanically, thickening shells or growing spines. Others took a more radical path. They turned their saliva into venom-got cone. Snails are the most extreme result of that experiment. Instead of a rasping tongue used for grazing, cone snails evolved a hollow, barbed toothed, disposable harpoon. It fires using muscular pressure, fast enough to strike fish in a fraction of a second. For scale, a human blink takes about 300 milliseconds. A cone snail strike can be faster than that, but the weapon isn't the tooth. It's what's on it. Cone snail venom isn't a single toxin. It's a library. Hundreds of small proteins, toxins H, engineered by evolution to target one specific part of the nervous system. One blocks sodium channels, another freezes calcium signaling, another prevents neurons from communicating at all. Think about that precision. Most snake venoms act like blunt instruments, causing widespread tissue damage or blood failure. Cone snail venom is closer to a remote control. It doesn't destroy the system, turns it off. This is why aquatic snails became more deadly than land snails ever needed to be. In water, prey can escape instantly. A fish doesn't need minutes, it needs milliseconds. Venom had to act faster than muscle contraction, faster than fear. So evolution stacked the deck. Some toxins induce instant paralysis. Others suppress pain, preventing prey from struggling. Others stop breathing entirely. Delivered together, they overwhelm the nervous system before the prey even understands it's been attacked. Here's the part that still unsettles. Biologists, cone snails don't all use the same venom. Each species fine-tunes its chemical arsenal. To its prey, fish-hunting species evolve different toxins than worm hunters. Even individuals can alter venom composition depending on context, defensive versus predatory strikes. That level of biochemical control is rare in nature. Land snails never faced this pressure. Air slows everything down. Plants don't run. Predators can often be deterred by shells alone. There was no evolutionary incentive to invent molecular precision weapons. But underwater, softness is a death sentence. Venom wasn't optional. It was survival. And once that door opened, evolution pushed it to terrifying extremes. because the same toxins that stop a fish's nervous system work just as well on ours, which raises an uncomfortable question. How did humans discover this danger in the first place? Because the next chapter begins when people stopped seeing these snails. As harmless shellzans started meeting them the hard way, it didn't begin in a laboratory. It began with a body in the water. In 1935, a young man collecting shells in the Philippines collapsed shortly after feeling what witnesses described as a sharp sting. There was no dramatic wound, no visible bleeding. Within hours, he was dead. Doctors were baffled. The shell he'd been holding, beautiful, patterned, unmistakably harmless looking, was dismissed as coincidence. It wasn, single quotes T. Over the next decades, similar stories surfaced across the Indo-Pacific. Fishermen, shell collectors, divers, healthy adults stung once, then slipping into paralysis, breathing slowed. Muscles stopped responding. In some cases, consciousness remained until the end. Culprit kept reappearing in reports. Cone snails. At first, scientists didn't believe it. Snails were not predators. They didn't bite. They didn't chase. The idea that a snail could kill faster than many snakes seemed absurd then. In the 1950s, marine biologists began observing cone snails alive. What they saw rewrote assumptions. A fish would drift too close. The snail wouldn't move. Then almost invisibly it struck. The fish froze mid-swim as if switched off. No thrashing, no struggle, just instant stillness. That moment was the crack in the story. Researchers realized the danger wasn't mechanical, it was chemical. One of the most sobering modern encounters occurred in 1982, when a U.S. serviceman handling a live cone snail was stung in shallow water. He reportedly felt numbness spreading within minutes. Breathing became difficult. He died before reaching medical care. There was no There still isn't. To put that speed in perspective. Severe anaphylaxis, a medical emergency, can take 15 to 30 minutes to become fatal without treatment. Some cone snail envenomations act in under 5. What shocked scientists most wasn't just the lethality, it was the selectivity. Victims often reported minimal pain, no burning, no swelling, just weakness, then paralysis. The venom wasn't attacking randomly. It was targeting nerves with surgical precision. That realization changed everything. Marine toxin researchers began isolating individual venom components. What they found stunned the field. Tiny peptides evolved to bind specific human nerve channels, better than many synthetic drugs. One of those molecules derived from cone snail venom would eventually be developed into a powerful pain medication, hundreds of times stronger than morphine, without the same addiction risk. The same chemistry that killed had the potential to heal. But here's the unsettling part. Despite decades of study, no one has ever seen a cone snail use its venom at full defensive capacity on camera. Human encounters are accidents-messed judgments made because the animal looks slow, fragile, safe. Which brings us to the next mystery. If these snails are capable of such precision and power, why don't they use it more often? The strangest thing about cone snails isn't how deadly they are, it's how controlled they are. In the wild, cone snails don't behave like indiscriminate killers. They don't lash out, they don't waste venom. In fact, most of the time, they don't sting at all. They wait, they sense, they choose. That choice is chemical. Inside a cone, snail's venom gland is not one venom, but many. Hundreds of distinct toxins, each encoded by a different gene. Think about that scale. Humans have about 20,000 genes total. A single cone snail species may devote several hundred of them just to venom or genetic real estate than many animals use for vision or immunity. And here's where it gets strange. Cone snails don't deploy the same venom every time. Studies show they produce different venom blends depending on intent. One mixture for hunting, another for defense, another still for large fast prey. This means the snail is not just armed, it's selective. Fish hunting cone snails use toxins that cause instant neuromuscular shutdown. Worm hunters rely on slower-acting compounds that prevent escape rather than immediate paralysis. Mollusk hunters use venoms that interfere with muscle coordination, forcing prey to relax and expose soft tissue. Same body, same shell. Completely different biochemical strategies. To put that complexity in human terms, imagine carrying multiple tranquilizer darts. each custom designed for a different species and choosing the right one in real time. That level of specialization explains why aquatic snail venom surpasses almost anything on land. Water allows chemical signals to spread instantly. Evolution took advantage of that, refining toxins not for destruction, but for control. Here's the holy shit realization scientists had in the 1990s. Some cone snail toxins don't just paralyze, they manipulate perception. Certain peptides appear to induce a false sense of calm in fish prey, preventing escape behavior before paralysis even begins. The prey doesn't flee. It doesn't struggle. It simply stops responding. This isn't brute force. This is neurochemical deception land. Snails never evolved anything like this because they didn't need to. Their food doesn't flee. Their predators are slower, visible, avoidable, but underwater, prey can vanish in a heartbeat. Venom had to work before fear could, and it did. Yet, despite decades of research, scientists still don't fully understand how cone snails regulate venom expression, how they decide which toxins to produce, in what ratios, and when. No brain scans, no behavioral cues, just chemistry doing the thinking. Which leads to a deeper implication. If evolution can turn a snail into a precision neurochemist, what else has water shaped in ways we barely recognize? Because the final chapter isn't really about snails, it's about what extreme environments demand on, what life becomes when survival leaves no room for error. We've never seen a cone snail evolve. Not the moment venom appeared. Not the first toxin. Not the shift from grazer to predator. What we see instead is the end result, a soft-bodied animal carrying one of the most sophisticated chemical arsenals on Earth. And that tells us something unsettling about evolution. In water, aquatic environments don't forgive hesitation. They don't slow things down. Heat dissipates. Chemicals spread. Movement costs energy. If you're small and vulnerable, survival favors strategies that act instantly and at a distance. That's why water breeds chemistry. Venom, toxins, neuroactive compounds, from jellyfish to pufferfish to cone snails. Aquatic life repeatedly arrives at the same solution. Don't overpower to don't injure interrupt. Cone snails represent one extreme of that logic. Their venom didn't evolve to kill humans. We're collateral damage. What it evolved to do was stop a nervous system faster than muscle can react. And in that sense, it worked almost too well. Here's the scale that humbles. Researchers. Cone snails have likely been perfecting their venom for tens of millions of years longer than the time separating humans from early primates. Every generation tested, every failure removed. What we see today is not innovation, it's refinement. And yet for all that time, there are things we still don't know. No one has ever witnessed a cone snail hunting in the deep sea, where many species live. We don't know how often they change venom blends. We don't fully understand how they avoid poisoning themselves. We don't even know how many cone snail species exist. Ones are still being described. Think about that. A creature capable of killing a human in minutes can spend its entire life unseen, buried in sand, leaving no trace but an empty shell. And that shell picked up, admired, passed from hand to hand, is usually the only warning. This changes how we think about danger. In nature, not all threats roar. Not all weapons are visible. Some of the most powerful forces on this planet operate silently, patiently, without drama. A snail doesn't look like a lesson in evolution, but it is. It reminds us that intelligence isn't always brains, that power isn't always speed, and that survival doesn't always mean being bigger or stronger. Sometimes it means being precise, invisible, unforgiving, somewhere right now. In shallow tropical water, a cone snail is waiting motionless, unremarkable, carrying a chemistry set more complex than many laboratories. It doesn't know what it is. It doesn't need to dot evolution, already decided.